Okay, in this lesson, we're going to talk about functions and some key characteristics of functions and ways to evaluate functions. So let's start off with domain. The domain of a function represents the set of possible numbers that may be put into a function. Okay, think the x values of a function. Okay, to find the domain of a function, start with the set of all real numbers from negative infinity to positive infinity. And then we're going to look for these common restrictions. Okay, so number one, no negative radicands. Anytime we see a radical sign, we want to take what's underneath it, and what's underneath it cannot simplify, cannot be a negative number. Number two, we can't have any zero denominators. Okay, when we have zero in the denominator of a fraction, math breaks. So we got to make sure we check our denominators. Make sure that we don't give an x value for our function that can make that equal to 0. Number three, if we have a log function, we can't take the log of a 0 or a negative number, so keep an eye out for that. Let's look at a couple examples. Okay, number one, we're asked to find the domain of this function. We've got f of x equals the square root of x plus 3. So, first thing I see, we've got a radical. Can't have a negative radicand, so let's take our radicand, which is x plus 3, and let's make sure it can't be negative. So let's set it greater than or equal to 0. Let's force it to be positive. Solve for x, we get x has got to be greater than or equal to negative 3. So in interval notation, our domain is negative 3 with a bracket, including to positive infinity. Okay, example number two. F of x equals the square root of x over x minus 5. Okay, now we've got a fraction with a variable in the denominator. We've also got a radical in the numerator, so we've got to be careful. We've got two possible restrictions here. Let's start off with the radical. So let's take our radicand. Let's set it greater than or equal to 0 to make it positive. So for right now, our domain can only be 0 or any positive number. Okay, now let's take our denominator. Remember, we can't have 0 in the denominator, so let's take that and set it so that it's not equal to 0. Solve for x. So x can't be 5. So while x has to be a 0 or a positive number, 5 won't work either. So we've got our number line representation here, where we've got from 0 on to all positive numbers, not including 5. And our interval notation, we've got to show that in two pieces. So we've got from 0 including to 5 not including, and from 5 to positive infinity. Okay, next up, range. So range is a set of all positive values, of all possible values put out of a function. So think the y values. You've probably seen this before in algebra class, our function machine. So whatever we put into our function machine is the domain, or that's our x values. Think horizontal values. So, okay, so those x values go into our function machine, and what comes out is our range, or our y values, the vertical numbers on the graph. So let's look at a couple of examples of finding the range. Now for now, we're just going to find the range graphically. So if we were asked to find the range of a function x squared, okay, first thing I want to do is graph it. We get our standard parabola that opens up. It's got a minimum value at the origin. And again, range, think vertical values. There are no points south of the x-axis. So we're not going to have any negative numbers. The lowest point, that minimum, has a y value of 0. So that's where our range is going to start. That 0 is included, and then every single y value has an associated x above the x value. So this piece keeps on going forever and ever in the positive y. So our range goes to positive infinity. Second example, if f of x equals 1 over x. Okay, we've got to be careful with these because we've got two of these pieces in this rational function. So let's take this piece first in our third quadrant. These values right here look like they're getting closer and closer to a horizontal asymptote on the x-axis. So that's from about 0, and then this piece looks like it goes down forever and ever. So this piece shows that the range starts, in a sense, at negative infinity. So those values continue to go forever and ever without end. And we've got a break here at 0. This piece picks up on the other side, on the positive side of 0 on our x-axis, and it goes to all positive y values. So that's this piece here. Okay, another characteristic of functions is continuity. So a function is continuous at a point if the graph does not come apart at that point. There are 4 types of continuity. The first one is continuous at all x. If you can draw the graph of a function, the entire function without lifting up your pencil, that function is continuous. Our example here is a linear function. All linear functions are continuous. Second type is a removable discontinuity, okay, or a hole. So we've got an example here of a rational function, and we're going to come across functions that look normal except for maybe a little hole here. So removable discontinuity, we say that's a hole at its x value. In this case, x equals 2. Type number 3, a jump discontinuity. This is non-removable. Our example here shows a piece of a function here with a gap separating it from the rest of the function. When we study piecewise functions in the next couple of days, we're going to come across some jump discontinuity. And type number 4 is infinite discontinuity. Again, non-removable, like jump discontinuity. You'll see this when we have vertical asymptotes oftentimes, where we've got one piece of our function that goes in the opposite direction as the other piece of our function. So they're going in opposite y directions on either side of an asymptote, and the gap between that is an infinite distance. Okay, so here's another example. We're asked to find the domain, range, and classify the continuity of this function. Okay, we've got f of x equals x squared minus 9 over x minus 3. Okay, so first, let's take a look at the graph. So we can punch it into our graphing calculator, and we'll probably see that it looks like a linear function. Okay, that's kind of strange for a rational function, but it happens. So if we go back to our equation, our function, then if we factor the top and the bottom, whatever we can, then we'll see in this case that we've got a common factor on the top and the bottom that'll cancel out, that'll simplify, so that leaves us with what looks like a linear function. Okay, that's why our graph looks like a line. Now, we want to find domain, range, and continuity. So if we start off with domain, okay, we start off with a set of all real numbers. We've got a fraction with a variable in the denominator, so we want to take that denominator, remove any values that would make that 0. So the only value you could put in for x to make that 0 would be 3. So our domain is from negative infinity up to 3, not including 3, then to positive infinity. To find our range, if we put in that value, which 3, that empty hole in our domain tells us the x-coordinate of our hole. If we plug that number into our simplified function here, then that'll tell us the y-coordinate of our hole. So that's going to be the missing piece of our range. So our range goes from negative infinity up to 6, not including 6, and then from the other side of 6 all the way up to positive infinity. Okay, lastly, continuity. Said about 10 times now. We've got a hole, which is a removable discontinuity, and it's at x equals 3. Okay, next characteristic of functions, increasing and decreasing. So functions can be increasing, decreasing, constant, or a combination of those. Let's look at a couple examples. An increasing function in blue here. If you go from left to right on your function, so kind of track your eyes from left to right, if the y values are steadily getting bigger and bigger, they're increasing. So that function is increasing on its entire domain. This function here in green is decreasing. If we go from left to right, notice that the y values are getting smaller. They are decreasing. So it's decreasing on its entire domain. Okay, if a function is constant, then we've got a horizontal line. Y values aren't getting bigger or smaller. They're staying the same. They're constant. Oftentimes, we're going to see a combination of increasing, decreasing, and constant in the functions that we're going to study. Okay, here's an example of the graph of 1. If we look at it, we can kind of see 3 distinct pieces of this function. We've got this piece here, and then at this point, it kind of switches gears and flattens out to this point, and then at this point, it drops off on the third piece there. So let's break up our function into those 3 pieces. If we look at this first one, remember, we're going from left to right. Then from left to right, it is increasing until it hits this point here. Okay, that point's associated, it looks like -1. So we can say this function is increasing from -infinity over to -1. Okay, so we always want to use only x values when we're showing our intervals for increasing and decreasing. All right, from -1 to +2, it's constant. So that's that second piece. And then the third piece, it's decreasing. Remember, go left to right, from 2 to +infinity. Okay, another example of a mixed or a combination of those. We've got function, again, we've got a piece here that looks like it's decreasing to this minimum point. Then it starts to increase up to this maximum, and then it looks like it decreases again. So let's break that up into 3 pieces. This piece here from -infinity to, looks like -3, it's decreasing. So from -infinity to -3. And then from -3 to this point, which has an x value of 2, this function is increasing. And then from +2 to +infinity, it turns around and it is decreasing again. Okay, one more. Boundedness. The boundedness of a function kind of correlates to its range. So if we think about a function that has no bound on its range, either in the positive infinity direction or the negative infinity direction, then this is a good example of one. Okay, it goes forever and ever in positive infinity, forever and ever negative infinity. If it's got a limit on it on the lower side of its range, if it's got an absolute minimum, then it's bounded below. If it's got a maximum, then it's bounded above. And if it's limited both above and below, then we say it's bounded.